Okay, so welcome everyone to the first of a series of three workshops on ggplot2, on data visualization with ggplot2. In this one, we're going to talk about sort of foundations of ggplot2, what the GG in ggplot2 stands for, grammar of graphics. I'm going to talk more about that. In the second installation of the workshop, we're going to look more at like the best practices of data visualization and sort of some philosophy of data visualization, or not philosophy, yeah, some sort of evidence-based ideas about how to do data visualization better and how that applies to ggplot2. So more about like customizing plots, making them look nicer, and convey data better. And then in the third part, we're going to talk about some extensions to ggplot2. There's hundreds of extension packages that allow you to do all sorts of things. And so we've got a few picked out that we think are useful for that, including making like multi-panel plots and potentially some other stuff. I'm not exactly sure what extensions we've decided on yet. And part of it depends on, if you guys have a strong request or something, we can add something to that. So the first part of this is going to be not necessarily related to any code, any R code or anything, talking about the grammar of graphics. And then in the sort of second part, we'll dive into like how all that stuff applies to ggplot and R coding. Sound good? Right. Let's see if my changes. Just made some changes. Hey, we have a date now. Cool. Felt like that was important for some reason. All right. So, well, first of all, actually, I will give you guys the link to these slides in case you want to follow along on your own screen separately from the Zoom share for some reason. I'll put those in the chat. Great. Please interrupt me at any point if you have questions or anything isn't looking right to you or making sense. Please let me know. So today we're going to focus on understanding what is the grammar of graphics and how has it inspired the design of ggplot2 and a number of other number of other data visualization softwares, not R packages, but just data visualization software in general often will have kind of a similar design. So the idea is if you learn a little bit about this grammar of graphics, not only you're going to understand ggplot2 better, but hopefully it'll like prepare you to use other sorts of data visualization programs that also kind of use the same or similar design philosophy. So we'll understand what it means to map data to aesthetics, kind of a weird phrase. Learn to plot different data sets on the same data visualization. Understand the relationship between a geom and a stat. Learn to customize scales and guides, and probably other stuff that I forgot to include here. So what is the grammar of graphics? Well, it is a book. This is a book by Leland Wilkinson that I think the second edition came out in 2005. And I have not read it. I don't think you need to read it necessarily to understand the grammar of graphics. This is more like about how to design computer software, right? So this is statistics and computing here. But these ideas, which I think started being formulated in the 90s, are kind of what inspired the design of ggplot2 and a number of other graphics softwares. So it's a book. It inspired the development of ggplot2. And it's essentially an alternative for having a different function for every possible kind of plot, right? So instead of having a function for making a scatter plot, a function for making a line plot, a function for making a histogram, a function for making a box plot, for a violin plot, for like every possible different plot, instead thinking about what are the common elements of all data visualizations. And so the grammar of graphics is a framework that gives you kind of an expressive language to layer different elements, combine different elements that are common across all data visualizations to create basically any kind of plot you want. There are limitations, but it's also extensible. So yeah, And the grammar of graphics has 7 components. And what we're going to do is go through each of these 7 components using this example plot here on the right and try to kind of identify those components and talk about what they are and what they mean. So those 7 components are data, aesthetics, scales, and guides kind of go hand in hand with scales, geometric objects, statistics, facets, and coordinate systems. So these are essentially the 7 elements that every data visualization has in some way. So we'll start with data. So data is observations and variables that are being visualized. So this is a data set called Polymer Penguins. It's a data set we use a lot for examples. So just looking at this plot here, what data is being visualized? What kinds of variables are being visualized? If you want to type something in the chat, you can, or if you want to speak up, let something out, that'd be good too.
Body mass and build length.
Body mass and build length, yep. Any other variables?
The 3 species comparing.
There's 3 species, yep. And I'll tell you that these are not labeled, but these are the names of islands that these penguins are. So there's something like 345 or something like that observations of these penguins. And yep, for every penguin, we've got body mass measured in grams, build length measured in millimeters, and we've got the island and species that they belong to. And these are categorical variables. So that's our data for this plot. So the next element are aesthetics. So aesthetics are visual elements. Think like color, shape, transparency, size, position, and others that are used to encode data potentially. So what aesthetics in this plot are being used to encode these data, these variables? Let me see.
Color.
Species.
I see color for. I heard color for species. Did somebody else speak up? What was the other one? Color and size. I see in the chat. Okay. Yes, these points and lines and things have a size. In this particular plot, it is not mapped to a bit of data, but it is. It's not representing data in any way, but it is an aesthetic. Yeah, it is an aesthetic that these elements have for sure. Size. What else? So I have just. Oh, go ahead.
I was thinking of the shape, the circle versus a square.
Mm-hmm. Yeah, shape is an aesthetic for sure. These points could come in different shapes. Definitely. The other one is position. So we often kind of forget that one, but yeah, just where these points are horizontally and vertically is an aesthetic visual element of those points that is, in this case, representing data, right? It's representing the body mass and the build length is how the position is used here. So color, X position, Y position are the aesthetics in this plot that are mapped, that are connected to data in some way. But we also have other aesthetics, like folks mentioned, there's size, there's shape, there's a lot of other potentials here. So these lines could be different line types, dashed versus solid lines. All those things are aesthetics, visual elements of these that can be connected to data potentially. Yeah. So scales. Scales translate data units into visual units, and guides translate visual units back into data units. So what does that mean? So for example, we can look at this scale along this x-axis here. So this is translating like grams here, so data units, grams, into visual units. So how far apart should 1,000 grams be, right? That's what a scale is doing. It's determining how far apart these values should be. And then the guide is what I just circled here. This is translating those visual units back into data units, because it's telling you that this distance right here is the difference of 1,000 grams. So it's translating the visual element, the distance on this plot in pixels, back into data units of grams. So the guide is these numbers and these tick marks. The scale is determining, how these data points are how far apart they are on this axis when they're 1,000 grams different. That's how many pixels apart they are. So what other scales are being used in this plot? Scales or guides?
Millimeters,
Say that one more time.
millimeters on the y-axis.
Yep. So we have similarly on the y-axis, we have a scale that's translating millimeters into pixels in the vertical dimension. And then we have a guide here that's telling us how to interpret that and translate those pixels back into data units of millimeters. What else? There's one other scale and guide combo here. We have our color also here. So there's a color scale involved here that is translating data units. In this case, it's a little weird to say units because it's a categorical data set, but we're looking at these 3 different species. They're being translated by this color scale into blue, red, and green. It doesn't have to be those colors. It could be other colors, right? But this particular scale, this color scale, is translating Adelie into red, Chinstrap into green, and Gentoo into blue. And then we have a guide over here. We also call a legend when it's for color or something like that. This guide is telling us how to translate those visual elements, those visual units of hue, right, of color, back into what it represents for the data. So back into Adelie, Chinstrap, Gentoo. So scales are taking that data, and we've mapped the species variable to the color aesthetic, but the scale is saying, well, which colors? Red, green, and blue. And the guide is translating that back for us. We've mapped body mass to the x-axis, but the scale is saying, well, how many pixels is a gram, right? How many pixels is 1,000 grams or whatever? And then our guide is our x-axis labels there that help us translate that.
Would the trend line be a scale as well? Since it's showing us some, some data. Like,
yeah, we'll talk about what the trend line is here in a second.
okay. Yeah, I was wondering if it's a scale or a stats. Anyway.
Yeah. So it's the scale. So it is using the same scale, the same 3 scales that we've identified, right? So the trend line is also showing us these are still in units of bill length, body mass, and the colors representing species. So that those 3 scales are applying to the points and to the line, but the line is not a separate scale, if that makes sense.
Gotcha.
So yeah, so we have, sorry, again, just to repeat it, continuous and linear X and Y axes, and we have a discrete categorical color scale in this plot. So talking about lines and points, we also have geometric objects. This is the next element. So these are objects that often have multiple aesthetics that represent data visually. So this is starting to get a little tricky to describe the differences just in definitions, because that definition sounds a lot like what we talked about with an aesthetic, which was a visual element that is used to represent data in some way. This is an object representing data visually. So what's the difference, right? So anybody want to take a shot here, and what geometric objects are we using in this plot? We are
The
using
tiny dots or circles, isn't
Yeah,
it a geometric object?
exactly. Yeah, we're using points or circles here, and we're using lines. I see in the chat Brian mentioned. Yeah, so we have lines and points. Those are our geometric objects. These are often called geoms in ggplot2. So if you use ggplot2, all these functions that start with geom. So there's geom point, geom line, geom whatever. So these are geometric objects, right? And so to keep this this idea separate from that of an aesthetic, we can think about how one of these geoms, like a point, has multiple aesthetics, right? Points have size, they have transparency, they have color, they have shape. Lines have the line width, they have whether they're dotted lines or solid lines, and they have color, right, and transparency. Those are all aesthetics associated with these geometric objects. So yeah, we have data being represented using the circles and points, and we have this trend line of some kind represented. So statistics. So statistics go hand in hand with geometric objects. But statistics are any calculations or transformations that have to be applied to the data in order to draw that geometric object. So are there any of these calculations or transformations that need to happen for this plot in order to draw either the points or the lines? So to convert fill length, body mass into position, for example. Another way to think about it here is these lines, right? How would we define these lines? Yeah, I see Brian in the chat said the points do not need to be changed, and that's right, right? So the points are a good example where there is no statistic needed. In ggplot2, we call this stat equals identity often, right? So the x position is literally the x position, the y position is literally the y position. We've got 344 observations here. And what about these lines, right? These lines, rather than having an x and y position, they have like an intercept and a slope, or you could think about them having a sort of a point here and a point here at the beginning and the end. So we have maybe an x and a y for the beginning and an x and a y for the end. So how do we get from 344 observations to the slope of a line, slope and intercept of a line? Do some kind of statistic. Any guess as what this one might be? No answers. Any guesses?
Correlation?
Could be a correlation, yeah. Could be a regression line or a correlation line or something like that, yeah. But we need to do some kind of transformation of the data in order to get some values where we can draw that line. So some kind of statistic needs to happen. And in this case, I used a linear regression to do this. So, but it could be, a line of correlation or something like that is also totally possible. Yeah. Okay, so the next element is facets. And not every plot has facets. So this is an element that it's not in every data visualization, the way that probably geometric objects are, and statistics might be. But facets are often seen to create what are called small multiples, where we kind of split the data out into subplots by some variable. So in this plot, what variable are we using to split it out into facets.
The islands.
Exactly, yeah, the islands. So Bisco, Dream, and Torgerson are islands. And so we're, in this case, faceted by island. But again, not every plot has this. We could have plotted all these islands together. And there would be no facets. We can also facet by two variables potentially, where there's like, for example, rows like this that represent 3 different islands, and maybe columns that represent sex. So that's another variable in this data set that we haven't plotted here, but there's male, female, and NA. So we could have sort of a 3 by 3 plot faceting by 2 variables is a possibility. And the last element of the grammar of graphics is the coordinate system. And this one's weird because we don't normally think about this because it's usually the same. Most data visualizations you make have the same coordinate system, but a coordinate system is how the spatial positions are represented, on a screen, on a 2D surface. So think like map projections, right? The globe is a sphere, and there are tons of different ways that you can unwrap that sphere and plot it in a 2D plane. There are many different kinds of coordinate systems, projections that can be used. In this case, this is not a map, right? We're not unfolding a map. We're just plotting X and Y, body mass in millimeters. Anybody want to take a guess at what this coordinate system is called? Where we just have kind of perpendicular lines that are evenly spaced.
This is a throwback to high school math.
Yeah. Yeah. Anybody have a guess? Cartesian, yeah, I see in the chat. Yes, it is. This is the Cartesian coordinate system. So this is the default in most data visualizations, and it's the default in ggplot2. But it's not the only possibility. So I had when I was a PhD student, I had a friend who was working on studying fish schooling, and so he had all these sort of top-down videos of fish swimming in schools, and he wanted to know under certain situations which way were they facing, which way did they point their heads, and that he measured in degrees, so in degrees of a circle, right? And so that is something that naturally lends itself to polar coordinates. And so he used in his data visualization polar coordinates. So rather than having an X and a Y position on a plot, they had an angle and a distance from the centroid, an angle and a radius, basically, to show where those fish were in space and which direction their heads were pointing. So polar coordinates can be useful, and this is something you can do in ggplot2. You can make these polar coordinate graphs, and then, like I mentioned before, if you're plotting geospatial data, then there's a number of different coordinate systems that can be used depending on your choice, I suppose. But there's lots of different ways to represent, the spherical globe kind of unwrapped on a 2D surface. So I want y'all to take a little time to practice this. So here is a plot. I will put the link to this in the chat so you can poke around with it. And let's take like 5 minutes to take a look at this plot and identify the 7 different components. So try to look at, what data are in this plot, what aesthetics are being used, what scales are being used. There's some interesting scales in this. What are the geometric objects? Are there any statistics that need to transform the data in some way? Is it faceted by something? And what coordinate system is being used? So yeah, take about 5 minutes. Think about that a little bit, and then we'll come back and chat about it, see what we can learn. Okay. So let's take a look at this. There's some interesting stuff in here. So first of all, our first element is data. What's the data set? What data are being presented? Oh, I see in the chat, health and income levels. Yep. So we have, yeah, life expectancy and GDP per capita adjusted for price differences. And what else? What other variables? do we have?
Population.
Population. Yep. So that is here, population. What else?
Country.
Yeah, we have the country, the names, the country names. Any other variables?
This is kind of confusing, but could the levels be considered data? But you know what I mean? That's
Yeah,
hard.
up here, yeah, I want to talk, we'll talk about these levels when we talk about scales, but yeah,
Yeah.
so the question is this a different piece of data? I don't know, maybe. We'll talk about this. So, yeah, we have these income levels. Anything else? Regions, I see in the chat. Yeah, Jay, there's color by region. I think that's it. So yeah, life expectancy, GDP per capita, this income level thing, maybe region, size, population, and population size, and yeah, the country. Okay, so let's actually, I think it would make more sense to next talk about the geometric objects, and then we'll come back to aesthetics, right? So what geometric objects or objects are being used in this plot?
Just circles. But
Yep,
the
we've
size
got
of the circle varies.
Exactly. Yeah, we have circles, and one of the aesthetics that they're using for these circles is size, right? So the size of the circle is mapped to population size. What other? We'll just focus on the circles for now. What other aesthetics are being used in the circles?
The color?
Yep. Yeah. So color is another aesthetic here, and that is being mapped to region in this case. So we're mapping that variable to color. We're mapping population to size. What other aesthetics do the points have, or circles? Yeah, position. Ujjal in the chat says, yeah, position. So the X and Y position is another aesthetic that they have. So where they are in this space is representing the income and the life expectancy here. Are there other geometric objects here that are being used? Any other geometric objects? I see Brian in the chat mentioned font. What about the font? Oh, I see line. We do have lines in here, yes. These, oh, interesting. Yes, I hadn't noticed that. So these lines, these dashed lines correspond to these levels, level 1, level 2, level 3, level 4. Yeah, so that would be a geometric object that is connected to data. Yeah, so in this case, it's I guess the x-axis intercept that is the aesthetic here for these 4 lines. Yeah, those dashed lines. What else? What other geometric objects are here? One other. So Brian mentioned font. So we do have text here. We have text being another geometric object. So if we think about in ggplot2 terms, there is a geom text function. There's this would be geom text. We've got a geom V line for vertical lines. We've got geom point for these circles. So yeah, text can be a geometric object. And for this text, what do we have? What aesthetics are being used for the text labels?
The population.
Yep, we have the size, the font size of the text being mapped to population. So the font size there is the aesthetic. Yep. And then what else? We also have position. Oh, somebody said all caps versus regular. We do have some that are in all caps, like USA, but I think it's just because they're acronyms. Is that what you're talking about, or is there something else? The labels are all caps. Oh, the labels, yes, down here. These sort of annotations, are in all caps. So is that representing data though? Is there some data difference between all caps and not all caps?
No.
No, right. So it is an aesthetic, I suppose, right? The case, like is it title case, is it uppercase, lowercase? I could imagine potentially a plot where all caps versus, title case represented some bit of data. That could be possible. I don't know that that would be, I don't know that that would be a effective data visualization strategy, but that certainly would be a possibility. But we also have like position, right, of these labels. So we have the X and Y position of these labels is sort of matching the points. It's not exactly, which is interesting, right? So they're offset from the points to make them more readable. But you can tell, you can connect them because they share the same kind of size and aesthetic, right? So it's pretty clear that China here is referring to this big red circle and not any of the many little tiny circles that are actually overlapping. Whereas if China was exactly on top, it'd be kind of hard to read. So these text elements here are not being mapped to data. They're not representing the data. They are more like a sort of an extra guide or an annotation, right? So they're just like a little extra interpretation of this guide down here for the x-axis scale. But yeah, we can definitely have like extra stuff on plots in addition, extra annotations. So I think we covered the geoms and the geometric objects and their aesthetics. Are there any statistics happening here that need to like to summarize or transform the data in some way?
I mean, this was also a bit like confusing to me. It's like I never thought about plots in this way. So like maybe like could I don't know, not the colors, but maybe the sizes of the circles, like it's not just oh, here's China up here and then another country, Ethiopia down there, and then they're not like same size. So it's kind of telling us a story by like a statistical story. I don't know, maybe. You know what I mean? Like we can correlate maybe like region to colors even.
Where a statistic might come into play, and I can't say for certain that it is the difference here between 1 and 1,000 million does not appear to be linear to me. Like if it's the radius of the circle or something, right? And this is radius 1 and this is radius 1,000 million. There's got to be some kind of transformation of the data happening to get from population size to radius of a circle or area of a circle or something like that. So I don't know what that is, but it doesn't seem to me like it's just literally the area of the circle is 1 versus 1,000 million, or the radius or whatever it is, right?
Yeah, like something's going on there, but I couldn't like really point.
Yeah, so there's probably some statistic involved in.
So it should be a correlation coefficient of some type of either regression or correspondence analysis that tries to find a relationship between health and income, right?
Yeah, in what way? In like, where does that show up in the plot?
Like we have to, okay, I guess there's no conversion because the axis, okay, we're not converting the axis, so we're just plotting, right? So we do see the relationship, but we're just plotting. Okay, never mind.
Yeah. So, but if we were to, so like we are just plotting literally, this is the income value on the x-axis and y-axis. But if we were to sort of fit a line to this or something, then we would need to do like a regression or something in order to get the values, the x and y positions for that line. So I think in this case, the only statistic we maybe need is something to translate population size into area of the circle or radius or whatever. Let's talk about scales, because I think these scales are pretty interesting. So what scales do we have We have several. What's a scale? Yeah, so Brian in the chat mentions what's up with these categories. So we have two x-axes kind of in this plot, right? We have down here GDP per capita, and then up here we have income level. So these categories, level 1, level 2, level 3, level 4, we are allowed to do this because this scale up here is just a transformation of this scale down here. So these are, I think, I could be wrong, but the way I interpreted this is that these are representing the same data. And that level 1 is just income below whatever this point is, 3,000-ish GDP. Oh, good, we have an actual thing in the chat here. Level 1 is less than $2 a day. Level 2 is $2 to $8 a day. Level 3 is $8 to $32, and level 4 is 32 plus. So we've taken this GDP, we've translated that into dollars per day, and we've then translated those dollars per day into these categories. So this is a different axis here, and it is just a transformation of this income scale. So this is a thing you are totally allowed to do in ggplot2 as well. What you are not allowed to do in ggplot2 is to have an axis, two x-axes where one represents totally different data. So we can't have like income down here and then up here have like mean annual temperature. That is not allowed. And the reason for that is because the creators of ggplot2 don't think it's a good idea for you to do that. So you could certainly draw that on a graph, but the problem there, right, is that it's confusing because you're not really sure, which points or which geometric objects correspond to which axis. But in this case, this works because it's just a transformation of income scale. So we have this kind of cool income scale down here and up there. Yeah, go ahead.
Sorry, just so two x-axis will not be allowed, but two y-axis are possible, right? Is that right?
Same thing, right?
Oh,
So
okay.
it's the same exact idea. You can have two y-axes where one is kind of a transformation of the other. So you could have degrees Celsius on one axis and degrees Fahrenheit on the other. That's totally allowed. But what is not really allowed is to have, degrees Celsius and then, millimeters of precipitation or something like that and plot both things on the same plot. Like that those graphs do exist. Yeah. But what I'm saying is in the ggplot2 package, you're not really allowed to do that.
Oh, okay. Thank you.
Yeah. And it's, again, just because designers of it have decided it's almost always not the best data visualization practice, can lead to a lot of confusion. And it doesn't fit well with this grammar of graphics kind of philosophy.
One question, Eric.
Okay, go ahead.
Yeah, go ahead, Jay.
Yeah, I see these large circles.
Yes.
Will the large circles always be, won't they hide something behind, or does R make sure that the largest one is always at the bottom and then as it
R does not do that, no, but you could do that. There are ways to control the order in which things are drawn. And I don't know that this plot was made in R, but if it were, then they would, have had to take some extra efforts to make sure there's not overplotting. Another possibility, so here they've probably taken great care to make sure that the circles are stacked in the right order, but it could also be that you add some transparency to this or something so that you could see through the big circle a little bit if it was hiding something.
Thanks.
Was there another question, comment? So the only thing, are there any facets? I guess I'll ask. Any facets on this?
I was going to suggest that income levels is a type of facet, but since I guess, I don't know, might be wrong, but since it's the same data, right? So it's not considered a facet.
A facet, yeah, a facet would be like if we saw 4 separate panels, one for each level that included only the countries in that level. So if this line were, if there were Right, so the reason it's not a facet, I guess, is because we don't have like a border here, and we don't have space between these, and this line goes right through the middle of some of these countries. So, but yeah.
Gotcha.
Yeah, at the website, I think you can hit play and show the data change over time, maybe a facet. Oh, that's an interesting idea. Yes, there is, and I'm not gonna, I don't know exactly where to find it, but there is an animated version of this. And yes, you could think of those sort of frames of an animation as facets that are being displayed kind of one at a time rather than all side by side. So, and one of the extensions that I think we're going to talk about in part 3 of this workshop series, it allows you to make animated plots like that one, where you have the data changing through time. You can make like a little animated GIF. And then our coordinate system here is just our regular old Cartesian coordinates. Nothing super exciting. So there's a lot going on in this plot, but we can kind of explain all these elements in terms of those seven elements of the grammar of graphics, in addition to some annotations, which I don't know, maybe that should be an 8th element. I don't know. But we've got annotations here, titles, labels, things like that, other stuff, captions and such. So we could, and we're not going to do this today, but we could, use our knowledge now of this plot to try to recreate it in R. And now that I say that out loud, I go, oh man, that would have actually been a really fun exercise. Maybe next time. But what we're gonna do now, I just want to take a little bit of a break. And then give everybody a chance to like stretch and get some water or use the bathroom or whatever. And when we come back, we're going to talk about applying these concepts to ggplot2. We're going to go through each one of these elements and see how it applies to ggplot2 and learn some cool like tips and tricks and things that are related to each of those 7 elements. So I'll see you in about 10 minutes. Go get your snacks, get some water. Going to move along to taking a look at ggplot2 and how all these things kind of apply. And I'm going to be talking about some examples and then kind of switching back and forth between RStudio and the slides and the typing code. Feel free to code along if you'd like. I will also like share after the workshop today. I'll share like a document with all the notes and code and stuff. If you'd rather just kind of watch or something, that's okay too. Okay, so next part, ggplot2 and the grammar of graphics. So seeing how all this kind of inspired how ggplot2 works. And if you've used ggplot2 before, you're probably already recognizing some of the connections to what we talked about in the first part. So we're starting with the first element, data, obviously very important. Data is the first argument to the ggplot2 function. So ggplot, they all start with ggplot function, and the first argument is data. So very important. And that data is usually inherited by all the layers. So usually what you do is you give it a data set, and then you maybe add some points and some lines and some other stuff. You add different geometric objects to it. But we can also use, we can override the data set for certain layers, and we can do something where we plot 2 different data sets in the same plot. And here's an example of that. This is a jitter plot. So these points are just kind of like spread apart randomly so that we can see them better, so they're not all on top of each other. We've got 3 different islands, body mass, and then this blue thing here is plotting the mean, and the bars are the standard deviation. So that's what we're gonna try to recreate here in RStudio. So we're gonna start by maybe up here. I will load our library. We're gonna load all the tidyverse because I'm gonna use some of the other things in there besides ggplot2, but ggplot2 is included in tidyverse. So we see it's loading all these packages. And we're also going to need Polymer penguins, which has our data set, penguins. Boom, there's our data set. So species, island, build length, build depth, flipper length, body mass, sex, and year are possible variables we could use. And so, like I mentioned, they all start with ggplot. And as you see in that little pop-up, our first argument is data. So our data is penguins. And then the next argument you'll see is mapping. And so this is where we define aesthetics using AES. So AES, if you've seen that before, that stands for aesthetics. So this is where we define how data variables are mapped to aesthetics. So in this plot, X is island, Y is body mass, X equals island, Y equals body mass underscore grams. That's all I'm going to do for now. Okay. So then I'm going to add a plus here, and we're going to do our first geometric object, which is those points. We'll just do those points for now. Geom jitter or jittering. And so we've got this. So that's our points there. So how would we add some of those error bars, right? There's a couple ways we could do it, but one way that I'd like to do it is with geom error bar. And if we look up the help file for this, we look question mark geom error bar and take a look at that, we can see what it needs, what aesthetics it needs. So in the help files for geoms, they've got all kind of the regular stuff that a help file for R has, but then they also have this section called aesthetics that tells you what aesthetics it understands and are required. So it looks like it needs an X position here, a Y position, sorry, an X position, and it needs a Y min and a Y max to define the sort of bottom and upper part of those bars. And then for the point that we want to put in the middle there, we need an X and a Y there, right? So we need to create some kind of summarized data set in order to use this. So this is not going to work like we want it to. If I run it, we get an error. It says it needs Y min, Y max. So let's hold off on that. And what we actually need to do is create a summarized version of that data set. So we're going to use some dplyr functions to do that. So for every island, we want to calculate, we want to calculate a summary. We summarize here. And we're going to get the mean mass, which will be the mean of body mass underscore G. And just in case there's any NAs in that, I'm going to say NARM equals true. I'll remove missing values for calculating the mean. And then we need the standard deviation, which is SD. Okay. So what does that give us? That gives us for every island a mean that we can use as a Y position. And then we have a standard deviation. So there's one more thing we need to do is get like an upper and a lower. So here I'll use mutate and say upper is mean mass plus standard deviation, and lower is mean mass minus standard deviation. And let's run that one more time. So now I think we've got all the values we need. We have the mean mass, which is going to be the Y value for that point. And then we've got the upper and lower, which can be our oh, I spelled that with too many P's. Let's fix that. We've got a Y max and a Y min we can use. And let's save this as ping underscore summary. So we'll assign assigned to that, the assignment operator. And so now what we can do is we can add our geom error bar, and we can override the data. So you see that there is a data argument here that is a possibility. So we can say data equals hanged summary. And now it's going to use a different data set. And we also need to give it those aesthetics it requires. So ymin is going to be lower, ymax is going to be upper. And now if we run that, oh, we get an error. Well, okay, so error caused by, in the second layer, body mass G not found. So we don't have in this data set something called body mass G. We have two choices for how we could deal with that. The one I'm going to go with is just override this aesthetic. So we've set it up here, y equals body mass G. But for this layer, we want y to be mean mass. It actually doesn't need it for geom error bar, but it's complaining because it's not in that data set. So check it out. We've got now our error bars on top of our points. And we want to also add a point for the mean. And so we're also going to use this panged summary data set. And we're going to say y equals mean mass. Okay. Now we got to make this look a little bit nicer, right? So this does not look like this yet. We need to do some things. So we can make the jitter layer look a little bit better by adding some transparency. So alpha is transparency here. And we can do maybe 0.4. That looks like. So that's a little nicer. This way you can see like where there's multiple points on top of each other because they're transparent. And you can also kind of see this point better for the error. We also could change the color of the error bar. So rather than mapping color to data, by including it inside of this AES, we can keep it outside and say just color equals blue. And we've got blue bars, and we can do the same thing for this point. Blue. And we can change the shape of this point to make it stand out a little bit better. Let's try square. And we can make it a little bit bigger, maybe. Size. Now I never remember what these numbers are in units of, so I'll just like start with 1. And 1 is quite small, so let's try 3. 3 is kind of big, maybe a 2.5. Pretty good. And then the last thing is these error bars are ridiculously wide. It's very silly. So we can hit tab here and we can see if we can figure out what it is. We've got an argument called width here. Again, I don't know what these numbers mean, so I don't know, I'll start at 0.5. I think it's the fraction of the distance across or something. So maybe 0.2. Yeah, that's pretty nice. There's one more thing we can do. Geom jitter, by what it does is it takes the point and it adds a little bit of random distance, x and y by default. But in this case, we want the y values to be accurate, I think. So what we can do is we can say height equals 0. And so that means don't jitter it the height at all. So now these are actually accurate values on the y-axis. I'm going to show a little trick here in RStudio, a little RStudio tip. In the code menu, there is a reformat code. The shortcut, the Mac at least, is Command-Shift-A. Windows, I think it's Control-Shift-A. And you can highlight some code and do that, and it'll like make it look pretty, or at least what it thinks is pretty. That makes it a little bit easier to read, where we have every argument on a separate line. So I see a question in the chat. What other functions, if any, be used in summary? You can do whatever you want in summary. That will provide what's needed for sufficient exploratory data analysis. Yeah, if we wanted to do instead of standard deviation, if we wanted to do you know, a median and some quartiles or something, we could add median mass equals median body mass G screw. We could do like the, you know, 10th percentile or something. There's a quartile function. What is it? Quantile function in R. Probs equals 21. You know, 90th percentile. Equals 9. See typo. So we could do something like this too. That's totally a possibility, although I just got an error. Missing values. Oh, I guess I have to say any true. So, you know, we could do something like this. We could use the P10 and P90 as the lower and upper, and use the median as the middle point. You can do whatever you want in here. And a little bit later on, I'll show you a kind of a shortcut way to do this using a statistic rather than using two separate data frames. Yeah. So the other thing I'll point out about this is we could have done it the other way. So I could have, instead of putting penguins in the main ggplot call, I could have put peng summary in there. And then I would have to supply the data argument just to this one layer, this geom jitter. So we could have started with the error bars and then added the jitter values. Would also be a valid way to do this. Two different data sets. So we can have two different data sets in the same plot. Obviously, they need to be like in the same units. So you know, if I can't plot you know, bill length for the error bars and body mass for the points, that wouldn't make sense because they're not in the same units, not in the same range. The error bars wouldn't be on top of the points. It wouldn't make any sense. But being able to override the data argument for certain layers is really helpful sometimes for plotting summary statistics or like labels or something, right? If we wanted to use a geom text to put some kind of label along here, we would create a separate data set that had a column with the label and a column with an X and a Y value, and we could use geom label or geom text to put that. Yeah. Cool. So, and like I said, we'll revisit this when we come to statistics and talk about another way to do this. Here we go. So here's the whole thing. I guess this is a different way to do it. Like I mentioned, using peng summary as the main data set. And so in this case, I didn't have to supply the data argument for geom point or geom error bar. And I only had to apply it here with geom jitter. So this is also a possibility. And, you know, I named things slightly differently, slightly different way. So, yeah, lots of ways to do everything. Questions about data? Talk about aesthetics a little bit. So aesthetics, we also kind of saw this example here where aesthetics are also inherited. So if you put aesthetics, the aesthetic mappings using that ADS function in the main ggplot function, it'll use the same aesthetics for every layer. But you can also specify them per layer. And you can set them as constants like we did in that previous plot where we just said color equals blue instead of mapping color to data. If you want to know all the aesthetics, there is a page here with all the aesthetics and all their possible values. So for color, you can give it a name, or you can give it this hex code, or you can this one cell package, lines. We've got the different types of lines. Line ends is an aesthetic, kind of a weird one. Points, these are all the different shapes they can have. These are their names. They can have fill and color and size and all sorts of stuff. So there's all of the aesthetics in ggplot2 and all the values they can have there. So what we're going to do now is a slightly different plot where we have the jittered points, but we want to put a box plot on top that has also the additional variable of sex. So here is an example where we've got the aesthetics defined up here, island and body mass, and we only have the sex aesthetic mapped to color for the jitter layer. So in this case, we get a box plot that represents, basically just it ignores sex, right? The box plot is ignoring sex. There's only one box plot per island here. And there's some other options for how that can go. So let's go back here. And we'll start with this plot, actually. I'll just copy and paste that into a code chunk. So let's say what happens instead if we put color equals sex up here. Let's get rid of this. So then we've got a box plot, separate box plot for every sex. And again, the values here, female, male, or NA in this data set. If we put color, if we override color, that's another thing we can do, is we could just say color equals green. That's ugly green. So setting a color to a constant value or setting an aesthetic, any aesthetic to a constant value is going to override any mapping to data here. We'll talk later on about what we would want to do if instead we wanted it still to be mapped to data, but we wanted to customize those colors. There's a different way to do that to a scale. There's one other option for how you could do this, which is notes real quick. Yeah. So you could do something like this instead. So what's going on here? This is similar plot. We've got island, body mass, and sex up here in the main ggplot call. And geom jitter is inheriting all of those, but we don't want geom box plot to inherit them. There's this inherit.aes argument. And so that's saying it's not going to look at any of these aesthetics, and you have to map all the aesthetics in that layer yourself. So that's another way to do it. But this way, like I have to repeat x equals island and y equals body mass. If I left those out, left one of those out, for example, it's going to error. It's going to tell me, well, it's actually not going to error. It's going to do something very weird and plot the box plot over to the side here. So I think if we got rid of this, it would error for sure, though, right? It needs y values. Yeah, the box plot doesn't even show up if you do that. Very weird. So inherit AES, just be careful with that. I guess it might save you some typing in some situations. But... So yeah, and then the other thing I wanted to show, which I guess I already did, is that if you look up, if you want to know what aesthetics are possible, you can just look up the help file for that geometric object. So I mentioned like geom text earlier. We wanted to know what are the aesthetic mappings that we could use. We can go to the help file and scroll down and see that we could map data to the X position, the Y position, the label, the transparency with alpha, the angle of the text. So is the text like horizontal or is it rotated in some way? That's an interesting one. Color, family, which is like the font family. So you could have whether the font is serif or sans serif mapped to data, I guess. Font face, like bold or italics. Group, Now, all of these have group. This is a weird one where kind of like color. So like how we have, actually, let me demonstrate that one because that's kind of interesting. So let's grab this here. So let's say for some weird reason, we wanted 3 separate box plots, but we didn't want them colored. In this case, this is not a great example because you wouldn't want that because you wouldn't be able to tell which one is which. Usually this is used for lines or something. But just to show an example here. So we'll say color equals sex. We'll take that out of the main one and we only want the jitter to be colored by sex. And we have to put it inside of AES for that to work. And we want 3 different box plots. So we can do AES group equals sex. And so this does kind of the same thing. It was very interesting. It's not exactly what I expected because it's not using the X values here. So kind of a weird example, but we are getting 3 separate box plots for the 3 sexes here. I suppose we'd have to do something like sex and island to get this to actually work right. Nope. Anyway, don't use it for box plots, but the group aesthetic is available for all of these. And HJust horizontal adjustment. So whether the text is above or below, I guess. Line height, I'm not sure what that one is. Size, we saw that in the Gapminder data set where the size of the text was mapped to population. And VJust is vertical adjustment. So if you want to know what aesthetics are available to map to data, they're in the help file in a separate section here where bold ones are required. So yeah, I'm just going to delete this. Maybe I'll put in a different example with the group aesthetic afterwards. Okay, scales. So scale functions affect the range and the breaks in scales, and also are the kind of main way of affecting the appearance of guides, including like legends for color and shape and things like that. The main way to change those is through scale functions. So we're going to go through an example where we're going to reorder and recolor a discrete color scale and change the number of breaks on the axis. So here is the like finished thing. So we have our 3 islands, body mass versus bill length. This is just like the plot we were seeing in the first part, but now we've got custom colors and custom breaks along the X and Y axes. So let's go through that one piece at a time, including starting with the original plot. So yeah, I'm gonna find the code for that original. Second here, got that notes. Copy and paste this and talk about what it is. So this is our original plot. I don't need to do the copy. So we start with the penguins data set. We map the X position to body mass, the Y position to bill length, and the color to species. We use geom point to draw the points. And then for that line, we use geom smooth using the LM method for linear model. And I'm saying don't draw a ribbon, an uncertainty ribbon around it. Just draw the line. And then we are faceting that by island. And that original plot, again, looks like this. So now what do we want to do if we want to customize the colors? So the first step is to pick out some colors. And you can do that with names or with hex codes, which you can like look up in a color picker online. So I have some colors picked out, and I'm going to do these as a named vector in R. So I'm going to call it my coals, and I'm going to say Adeli. I want to be And I'm just copying and pasting this from my notes. But you would probably copy and paste them from some kind of color picker online. So we're going to use this kind of purple color for a deli. Chin strap equals. Oops. This orange color, and then into the last one. So this is how you create a named vector in R. You have the name on the left equals whatever. So we need this in order to say which colors go with which levels of species. Then we're going to take our plot key, and we're going to add another layer to it. We're going to add scale, color, manual. Now you see, I'll just stop here. I just typed scale, and you see there are a lot of scale functions. so many. We're going to use scale, color, manual. And let's look at the help file for that. Scale, color, manual. You see there's also British spelling as an option. They do the same thing. And for the arguments, we have ... values, civics, breaks. And so the ... is arguments passed on to discrete scale. I could click on this to see what else is available, but we're actually, excuse me, in this only going to use values and breaks. So values is how we change the colors. So if we do that, now we have our custom colors, purple for deli, orange for chin strap, green for Gen 2, right? Now we want to change the order of these as well. We want maybe them to be in sort of the order that they appear on the plot. So maybe Gen 2 at the top of this legend, and then chin strap, and then a deli. And we use the breaks argument to do that. So breaks is like for a discrete scale, like something categorical, it's just kind of the order of how they appear. For a continuous scale, it's where these are the breaks, right? Where there's tick mark placed is a break on a continuous scale. So here we're going to say we want it in the order Gen 2, belly, then chin strap. And so that C has changed the order in the legend here. This is also a place, this is one of a couple of places where we could set the name of this legend. So maybe we want that S to be capitalized in species. So we could do that too. Cool. Any questions? I feel like this is a common thing that people want to do. This is one of the first sort of customization questions is how do I change the colors? This is how you do it. Okay, so now we'll move on to the breaks and the X and Y axes. So just like there's a scale color, there's a scale X, and there's a bunch of them actually. We have continuous data here, so I'm going to use scale X continuous. If we had dates, it'd be a little bit different. Time would be a little bit different. We could reverse the scale if we wanted to. Lots of options in here. We're just going to go with scale X continuous. And there are two different ways to do breaks here. So there's a breaks argument and there's an n.breaks argument. So the n.breaks argument is to say, give me about 10 breaks. So we'll run that and see what it says, see what it does. So how many breaks do we actually have? 1, 2, 3, 4, 5, 6, 7. So not exactly 10. But what it's done is we've said, give me about 10 breaks, and it gives me about 10 that are at sort of pretty numbers. So it's not going to do weird decimal places. It's going to be nice kind of whole numbers placed along there. So, if I wanted fewer, I could say, give me about 5. And it's going to give me 1, 2, 3, 4 breaks. I said, give me more, 15. 1, 2, it's about 15. And again, see, they're like nice whole numbers. So n.breaks is great if you just want to kind of have more or fewer breaks, but you don't care exactly where they are. Now for the y-axis, let's demonstrate setting some exact breaks. So that is using the breaks argument. So here we need to give it an actual sequence of numbers. Weirdly, they don't need to be evenly spaced. So we could give it like 45 and 60. And it would do that. It would draw lines just at those two, right? So could be 41.123 and 60 or something like that. And it would do that. That's usually not what you want to do. Usually you want to plot, provide some kind of sequence here. So I'm going to use the seq function to say, let's go from, something before that looked pretty interesting. So from 30 to 65 by, I don't know, 5.5, just to demonstrate. So this is now giving me an exact sequence here from 30 to 65 by 5.5. Now it's not labeling 30 and it's not labeling 65 because those are out of the range of the data here. So it's like smart enough to do that. We could change the limits to expand that range if we wanted to. So let's say limits is 30 to 65. And then it would kind of expand it out a little bit. Yeah. And so you notice that changing those breaks also changes the grid lines here. So that's a good way to do the grid lines. There's also a minor breaks argument here that you can provide a numeric vector also. So the minor breaks are the lines in between these tick marks. So that is one way that you could adjust those or make them go away, is potentially with scale. It's the only way. Charlene in the chat asked, I thought I saw log in there. With this one would normalize data. Yeah, so there is a scale log. So let's just see what that does. So here's our data set with this scale x continuous. We can do scale x log base 10, for example. And what we get is tick marks that are on a log scale. So this is not transforming the data. It's giving us a nice scale that is on a log scale. So this is really helpful if you have data that is sort of exponential and you want to just show powers of 10 on the scale. And there's also, I believe, there's ways that you could do X. If we wanted to so the labels, you can give it a function that returns different labels, thinking labels equals, there's the scales package. I never remember which one is scale log, label log, maybe. Maybe I put this in breaks, actually. Breaks. No. Sorry. Trying to do something that I don't actually know quite how to do. But there is a way. Oh, there we go. Yeah. So there, now we've got it just labeled like 10 to the power of, which is just kind of a neat, different way of labeling it. So there's lots of options here for the labels thing. There's a scales package that has all these label underscore functions that usually go well with a scale for different ways of labeling. Okay, that scales basically did the same thing as this with some extra stuff. So our next element is geoms. We've used a bunch of geoms already, but every geom has a default stat, but that can be overridden. And not all geoms use the same aesthetics. We've seen that already. And we're gonna look at the anatomy of a help file a little bit. Actually, we've already kind of done this. So we've seen this already. But we didn't look at what is the stat here. So let's just take a look at one of these help files and see what the stat is. So if we look for geom point, which we've used before, we see here that the default stat is identity. So this, as we talked about before, this is when there's really no statistical transformation needed. But for something like geom box plot, we did need some statistical transformation, right? So that box plot is plotting a rectangle for the so lower and upper quantiles and quartiles. It's plotting a line for the median. It's got these fences. So there's a bunch of calculations happening. And so we see that there is the default stat is box plot. And there's also, for every one of these stat arguments here, there is a stat function. So we could also use stat box plot, which has a default geom of box plot. There are certain situations where you might not want to use the default geom that comes with the stat. I have an example that later on when we talk about statistics, it kind of gets at that. But yeah. Okay, so this is just a little example I'm just showing here. We're not going to run through this, but this is just like a kind of demonstration plot of not all of the statistics that geom point, or all the aesthetics that geom point has, but we can map data to X, Y, color, shape, size, alpha, stroke. That is like the thickness of the line in some of these symbols, not in all of them. And I just have a note here, with great power comes great responsibility. So yes, you can map all these things to data. Should you? I don't know, probably not many of them. Some of them are ones that, would rarely make sense to be mapped to data, like, typeface or font for a geom text or something like that is probably not going to be the best way to represent data in many cases. Maybe. Okay, so stats. So every stat has a default geom, just like we saw. You usually use the geom function and not the stat, but you can use either one. We can use stat box plot instead of geom box plot, and it works. There are some stats that calculate actually multiple values that are available using this after stat functions. That's one example I'm going to show. So we're going to see a different way of adding a mean and standard deviation or some other kind of summary statistics on top of a jitter plot using stat summary, which does not really have a corresponding geom. And we're going to see making a binned density plot with geom histogram. So here's our stat summary. Let me just copy this, actually walk through it over here. So an alternative to creating a separate data set for our summary data is to use stat summary. So if we run just this here, ggplot and the geom jitter, we get our familiar jitter layer. And if we want to add a summary layer, there's another way to do it. So stat summary. I love stat summary. It's great. It's saving me a lot of time. So stat summary here, you see the default geom is point range. So not the same as the error bar, but point range has a point and a line, and it's basically the same. It just doesn't have those caps on top of the error bars. And the way it works, so if we actually just take everything out of this for a moment, take it all out, and I hit go on this, we get, it's very hard to see, but there are some teensy tiny error bars there poking out of the circles. And that's because by default, it is using the mean and the standard error. So standard error is like standard deviation, but corrected for sample size. And we have a really large sample size here, so small error bars. So what if we want to use some different summary function? We can do that. So in fact, let me just take out the jitter so we can see it better. Yeah, there we go. So you can see now the error bars. So this is just plotting means and standard error of the mean. So what we need is to supply a different function to do the summarizing. And we can do that with this fun.data argument. So this is a function that gives the complete, that you give the complete data and it returns a data frame with columns ymin, y, and ymax. So we could use any function for that. And one option that comes with ggplot2 is this mean underscore SDL function. So there's several of these kind of summary functions that are kind of built in. And you see that they are wrappers around functions from the HMISC. And so these dots are other arguments passed to the respective HMISC function. So mean SDL, what does it do? So if we just give it like 100 random numbers, what do we do? There we go. It gives us a data frame with columns y, ymin, and ymax. Now this has, if I follow these dots, here we see that there's another argument here, mult. So that is multiplying the standard deviation by 2 by default. So actually, if you wanted just one standard deviation, we have to say multiple 1. But we could write our own function that does this too, create our own thing or use some different one. And so that's why we need to do fun.data equals mean SDL. And fun.args is like a weird way of passing arguments to that fun.data. So we need a list, and we're going to say mult equals 1. That's our argument that we're passing.
Hey,
And
Eric.
so now we've got bigger error bars. Yeah.
I was just, there was a question in the chat about, is
okay.
there like a list or something about like what other functions there are beyond mean SDL? I poked around and couldn't find any.
It's weirdly hidden. So you do get, we run it with just, let's see, what is it? So it gives you a little bit of a hint here just by saying, oh, it's defaulting to mean underscore SE, and then you can like look mean underscore SE. And yeah, that doesn't really bring you to the page. It's not summary. I know, I wish there was a better description of how to find these. In the examples, there's a bunch of possibilities. So this is I think how I kind of figured that out. So if no aggregation functions are supplied, it will default to mean underscore SE. And then in the examples, you see there's like a mean underscore CL boot. And if we look for that, we get to this page where there's these 4 possibilities. So this is the mean and a bootstrapped confidence interval. This is the mean and a confidence interval from a normal distribution. This is the mean and standard deviation. This is the median and some high and low level. So you give it, yeah, you give it like a, you want it. So this is like a return basically quantiles that contain 95% of the data. Yeah, it's hard to figure these out. It's hard to find them for some reason. Wish the documentation was a little better, but it could be any function. So you can create your own function to do this as long as it returns a table, y and ymax. Good question. Let's see now what that looks like with the jitter. There we go. And we can do the same thing that we did before, and we can say color equals blue, shape equals square, size equals, I think we said 2. Oh, no, not 2.5. Goodness. Let's try 1. So the size argument, I'm never sure what the units are here. Maybe 0.8. Yeah, that's not bad. So we've kind of done the same thing as before, where we've overlaid a measure of central tendency and distribution, but in way fewer lines of code. It does like require there being some function that already does what you want it to do. But you could write your own. I think an example of that. I can't remember. Yeah, I'll just copy and paste from my notes here. here's a weird one where I want to plot the median and the 10th and 90th quantile of the data or something. So all I have to do is I have to have a tibble here, so or a data frame. This could be data.frame also works. We're writing a function, so functions in R start with the function, and then some curly braces. So we're creating our own functions. Now if I do median 80, and I get 100 random numbers, it gives me a data frame with y, min, y, max. Anything that gives you a data frame with y, min, y, max. And then we could change this up here to be median 80 instead. Now we don't have these arguments, right? And now it's plotting the median and the middle 80% of the data points instead. So you can't do a custom, but you have to write a function. Okay. So the other example I wanted to show is related to a histogram. So copy and paste some code here. So let's make a histogram of body mass. So geom histogram, lots of histogram. Let's do just that part. So here we go. We got a histogram. And we can facet it by island. So we have a histogram for every island. So now it's binning the body masses and it's giving us on the y-axis how many observations are in each of these bins, giving us an idea of the distribution of data. We can see from this that there's just fewer values on Torgerson Island. There's just fewer observations. This whole thing is smaller. If we added up all the counts, it'd just be fewer. So that makes it a little bit difficult to compare the distribution of body mass. And so if we're really only interested in the distribution, instead of a count, we might want a frequency or something like that. Something that where each of these kind of adds up, the area under the curve there all adds up to 1 for each island. And that is a possibility, and it's actually really easy to do. So if we look again at geom histogram, we can see that here it is, geom histogram. The default stat is bin, and stat bin here, the default geom is bar. And we can go through this help file, and there's this special section here on this one called computed variables. So computed variables are the variables that are going here on the y-axis in this case that are available. And so by default, it's giving us count, but we also have available to us density and count and density and width to play with. And so we can use these, we can access these with this after stat function. So if we want to change this histogram into a density plot, instead of just letting it do the default thing of having the y variable be count, we could say in here in the AES, simply y is after underscore stat density, for example. And now when we plot this, it looks a little bit different. Here, let me put them side by side. So this y-axis is density instead of counts of observations in each bin, and the density of points. So all of these values, basically, if you took the value of the tip of all of these, they all add up to 1 in each of these panels. So now this is a little bit easier to compare without kind of ignoring sample size differences. Right? So it's sort of, we can see that there's a much kind of broader distribution of body mass on Disco Island compared to the others. It's kind of a more narrow distribution of ignoring sample size. So there are, I don't know off the top of my head which stats have different things available like this with this after stat function. The one that I've used before is histogram, turning a histogram into a density plot. But it is, yeah, kind of an interesting option. Width is a weird one. You could potentially make the width of the bins, I guess, relative to the number of values in them. I'm not exactly sure how that would work. I think this is maybe not geared towards a histogram, but something else that uses stack data. So there's our density plot again. Yeah. Facets. So facet wrap and facet grid are the two ways to do facets. And I'm not going to talk much about these because I think we're going to see these more in part 2. We can talk more about small multiples and see some examples of doing this. And the last element is coordinates, coords. So coord Cartesian is the default for ggplot2, and you can adjust x and y limits in coord Cartesian, for example. And doing that adjustment in coord Cartesian is different than adjusting the limits in scale. So we saw very briefly, I showed adjusting the limits in the y-axis scale with scale y continuous. Adjusting them in coords is a little bit different. We also have coord polar for our polar data, like I mentioned before. Coord SF. SF is for spatial features, I think. And that is one that you would use for maps. And I'm going to show an example of how to kind of zoom in data, what happens differently. So we'll do this interactively here. So code. Okay. So for coords, we have our base plot again. P. Looks like this. So let's say we want to zoom in on a portion of this x-axis. What happens if we do that with scale x continuous? So if we take our plot and we do scale x continuous, we can set the limits in here. So we can say limits equals, we give it 2 numbers. Let's do 4,000 to 5,000. So we're zooming in just on this chunk in the middle. And let's see what it looks like. So some things to notice. This line here is sloping up gently. Now it's sloping down. What do we think happened here? Why is that line sloping a completely different direction? So here's our original plot again. We're zooming in on just this bit here through 4,000 to 5,000. We've got positive slope. We say limits between 4,000 and 5,000. And whoa, we have a negative slope. And we have a bunch of warnings. Why would that slope? Guesses. Yeah, Yoonhee in the chat says the line looks like it got drawn again, or drawn again, yeah, based on the data. And that is exactly right. So what's happening when we do this scale x continuous is it's removing data that's outside of that range and then drawing a plot. And so that's happening actually before the geom smooth is doing its statistics calculation to create that line. So the line now is only based on these points. So you also see that the line, like, it ends at the earliest point. So let's see what happens when we do it with coord Cartesian. We do coord underscore Cartesian. So we have lots of coord options actually here. So there's actually more than I mentioned than just polar and SF. We have actually a lot here. But let's look at coord Cartesian. Xlim equals 4,000 to 5,000. And let's see what it looks like. So very different. In our warning, we see removed 2 rows. It's been saying that all along. If we just run the original data set, That is just because there are 2 NAs in there. So the warning doesn't change. On this one, it said, remove 228 rows that were outside of the range. So it's not removing data. If we use the xlim and ylim arguments for Cartesian, it just zooms in on those coordinates. So it's not changing the scale. The scale, remember, is like part of what the scale does is determines the range of data that's shown and how it relates to visual elements on the screen. So how many pixels is a gram or 1,000 grams or whatever. The coordinate is just zooming in on the coordinate there, coordinate system. And so we have the line is the same slope, and you can see that stuff continues and is even cut off at the edge of the screen because no data points are being moved. So even though these data points are like technically below 4,000, the centers of them, the edges of them are still spilling over. Other things we can do with coords, I'll just briefly point out 1 or 2 of these. We have a chord fixed. This is if you, this doesn't make sense for this plot at all, but if you had variables that were in the same units on the x and the y axis, and you wanted those to be the same ratios, like the same distance between a unit down here and a unit up here, you could use chord fixed. In this case, obviously, it squishes things ridiculously because we have a range of thousands going across this way and tens going this direction. Excuse me. But that's available. There's also there's also coordinate transformations that you can use here. And this is, I did not really prepare an example for it, but let's try it. So let's try this. Does that work? Quotation marks? There we go. Maybe not. Did that do something? Let's look at the examples for quotation. So I'm showing this because there was a question earlier about the log 10. Yeah, that is the way to do that. So this is transforming the coordinate system. Maybe actually it would be more visible if we did the y-axis here. It's hard to see on this because of faceting, I guess. But we are actually, in this case, warping the coordinate system. So these lines are, I believe, slightly curved now. So doing a transformation in the scale, axis scale, just changed like where the labels were. Doing a transformation in the coordinate is actually like warping the coordinate system. So we could even. Yeah, so now this is being plotted on like a log scale. What if we do third? Might be more obvious. I don't know. This is not the best example, obviously. Let's try the example that's in here. So the original plot in their example looks like that. And then we can have these 2 different options for transformation. So we can see that the data points are actually changing where they are and that this scale is getting squished at the bottom. So this is actually warping the coordinate system versus doing the transformation in the scale, which was just changing like which points were labeled, which breaks were labeled. It was just changing how the breaks were labeled. So if you like already had log data that was on a log scale and you wanted to just have the breaks, you would use transformation in the scale. If you wanted to actually like plot your data differently on a different coordinate system, a log coordinate system, you could use this coord trans log 10 or something. So. Cool. That's the 7 elements. in ggplot2. So hopefully you've seen some interesting examples and learned some cool tips and tricks along the way. And hopefully now some of the stuff in ggplot2 makes a little bit more sense. Like, why is the function called AES to map data to pieces of the plot? Well, it's because it stands for aesthetics. Why do we have these geom underscore, stat underscore, coord underscore, scale underscore? Well, these all relate to this grammar of graphics, language, philosophy, whatever you want to call it. So I'll just wrap up here by sharing some links. So here we've got a nice book about ggplot2. This is the 3rd edition of the book that is kind of in progress, but if you want to learn more about ggplot2, that's a great place to go. There's also this really nice R graph gallery where you can see a variety of different types of plots and see R code that's associated with them. So if you want to know how to make a pie chart in ggplot2, you can do that, I think. Maybe they don't have an example for ggplot2, but they have examples in R for a lot of these things. And we're gonna, I think, see more of the R graph gallery in session 2 this series. There's also the official ggplot2 documentation, which is just the help files and vignettes that we're seeing. But the nice thing about them is that all the examples are run, so you can see like visuals for all these things. So, if you want to know, hey, what can I do with a geom dot plot? You can click on that, scroll through it, and you can see all these worked examples, and you can spot something and be like, hey, that's the thing I want to make. You can see how to do it. We also have our drop-in hours on Tuesdays at 9 a.m. They're virtual. You guys are welcome to join time and ask questions about ggplot2 or about whatever, or just hang out. I also wanted to remind you that we also have a data science incubator program where you can work with us to come up with a project plan for some kind of data science project and work with us. Provides kind of up to 80 hours. This is pre-funded, so free basically for anybody in the ALVSCI acronym, so the College of Agriculture, Life and Environmental Sciences or extension offices. And there's some examples here on our website of past projects that we've done, so you can get some inspiration. And yeah, with that, thank you all for sticking around, and good to see y'all. I'm happy to stick around for a little bit and answer any questions, but otherwise you're welcome to go and go forth and make cool data visualizations.
Awesome. Thanks, Eric.
Yep. See, we got some stuff in the chat here.
Thank you, Eric.
Yeah, you're welcome. Charlene says, off topic, but my data is like King Ghidorah and not the cute penguins. Gentle data cleaning, metadata merging, object extraction. Nice data like the penguins. Yes, so there's a lot of data cleaning that has to happen before you get to a data set that is right for working with ggplot2. ggplot2 does expect tidy data. And I did mention that. We have some other resources from like our fall workshop series about tidying data and some other previous workshops we've done. And it's always something we can help with in drop-in hours. So yeah, it's like most of the work is just tidying up your data. So. Oh, Brian, glad things helped for you. Yeah.
Hi, I just have.
Yeah, go ahead.
I have a really kind of unrelated but related question. I can also come to the office hours as well, but I was following up like some of like the facets and some of the aesthetics, and I had like a really stupid parentheses error, and I didn't see it for like 5 minutes, and I was trying to troubleshoot it, so I missed like a brief part of like some of the stuff with the scales. Are you guys allowed to share the code that you did today, or should I try
I'm
like...
gonna send a follow-up email.
Oh, okay.
To everyone. You'll have a link to the slides. You'll have a link to, so the thing I was copying off of is this here. So this will be available as this website. You can also download a PDF of it if you want as like a cheat sheet. Yeah, I'll send this all out in a
Awesome.
follow-up email later today or tomorrow.
Okay,
depending on how
sounds
long
great.
it
Yeah,
takes for the
thank
video
you.
to process. Yeah,
Appreciate it. Have a great day.
yeah, you too. All right, well, I'm going to take off. Is there anything else? Or
Enrique,
Jay,
I've got one
do you have a-
question.
Yeah, go ahead.
I'm trying to do some things, with R, but the GUI that I see on my computer looks very different from the one that you were showing, and as you coded. Is it straight R that you've installed on your computer?
This is RStudio. So RStudio is a integrated
Yeah.
development environment for R, and I
There you go.
highly
Okay.
recommend using RStudio. So you have to install both R. We often
Right.
say R is like the engine and of the car, and RStudio is like the dashboard. So like you
Sure.
can go directly into the engine compartment and push on levers and accelerate and all that, but it's usually not a good idea. Or it's more convenient to do it from inside the car. So yeah, I would highly recommend installing RStudio. And then you've got these kind of 4 panes. You can open up an R script where you can type your code here and run it from here. And then what you're doing basically is working direct just in this pane. This is R, down here is the R console. So you can do stuff down here, but it's much better to have it in a script somewhere and then be able to run it.
All right,
and then
we'll
you've
do
got all
that.
these other wonderful panes showing you all the objects in your environment and help and all that stuff and your files and plots and things. So download RStudio, try it out. Should make things a little bit nicer.
Thank you.
Sure thing. All right, we'll see you later.
Bye-bye. Sure.